Hello everybody, I'm here with a video which relates to statically indeterminate structures. So the first question is, what is a statically indeterminate structure situation? Basically, whenever the number of unknown reactions in a problem is more than number of useful equilibrium equations, then the problem becomes a statically indeterminate. So for example, I'll give you a very simple example. If you have a beam, a simple supported beam, right, with some kind of loading acting on it, and if you call this pin A and this is roller B, how many reactions we have? How many unknowns we have here? We have two unknown reactions at the pin, right, AX, AY, and one unknown reaction at the roller, right? And basically, then we have three unknowns, and we have three equations. The equations being the two force equations and our moment equation for a two-dimensional rigid body problem. But imagine now if you become conservative and you put another roller here, say at point C, then you have an additional reactions. So now you have four unknowns, which is more than three number of equations that you have available. So this is definitely statically indeterminate problem if you put an additional roller. All right, so of course I'm not going to show you a problem like this. I want to show you problems that are related. Actually, this problem could be solved by using deflection, concept of deflection, which I'll probably show you another video on this. But I want to concentrate now on a problem such as, and I want to show you three problems and show you how you can handle this. A typical problem is that if you have maybe two bars or even one bar, actually, two bars made of different materials, different lengths, right? And then maybe they are connected to each other by a coupling here. So actually, let me call this A, B, and C, and call this 1, call this 2, right? Bar number 1 and 2. Let's say in this case, we have the same cross-sectional area, so area 1, same as area 2, and the same material. Modulus of elasticities are the same, right? Now, let's put some numbers here, guys. What if I load this by a 10 kilonewton load, right? And let's say this looks like as if this color is in the middle. Let's say this is 0.4 meter and this is 0.6 meter. How about that, right? Even though it doesn't look it. And I apply this, and I want to know what kind of reactions are developed at the support A and a support C. So you notice that there are two unknowns here. There would be a reaction opposing the direction of the applied load, both at A and C. And actually, RA is the same as the load in bar 1, F1, and RC is the load in bar number 2. You can call them F1 and F2. And in this case, there is only one equation, guys. The equation is balancing the forces in the x direction. So the sum of the two reactions must be equal to 10 kilonewtons, or F1 plus F2 must be equal to 10 kilonewtons. So only one equations, but two unknowns. The unknowns are RA and RC, or F1 and F2. So how do we solve this problem, guys? This is where the deformation, elastic deformation comes in. You see here, if you look at this bar and put force 1, because this bar AB is in compression, right? This point B is going to move there, and delta B is going to be FB or F1, right? Or RA or F1, the force in that, times the length divided by EA. Now, remember, they're made of the same material. So this is L1, by the way, I'm referring to, and this is L2, let's say, right? Similarly, for bar number 2, right, or BC, same thing happens. This guy is in tension, so B is going to move this way. The same deformation, guys. But this one is due to force number 2 times the length number 2 and divided by EA. So now if we set them equal, let me go to the other page. Delta B, which is equal to F1 L1 over EA, is equal to F2 L2 over EA. Of course, EA is going to get cancelled. L1, remember, was 0.4 in the picture, and this is 0.6. So 0.4 F1 equal 0.6 F2, or F1 equal 1.5 F2, right? Our other equation was F1 plus F2 equal 10, right? So clearly, when you solve this, and it's very easy, instead of F1, if you put 1.5 F2, right? And you get 2.5 F2 equal 10. So F2 becomes 4 kilonewtons and F1 becomes 6 kilonewtons. So you see how we use the geometry, or not geometry rather, but the elastic deformation to establish a relation. So basically we said that the movement of point B, which causes, for bar A is the compression, is the same as the tension that is developed in bar number 2. Okay, so this was our first example. Let me move on and show you another example. So the next problem I want to show you is one that I would use geometry. So let's say you have a vertical beam or bar pivoting about this point, which I'm going to call point E. And then I have two wires that are holding this, wire AB, right, and wire CD, right, and then a load that is applied right in the middle of this section AC, let's say 600 pounds, okay, and I'll give you some dimensions here. Let's say this is a foot, this is, let's say, also a foot here, and this is a foot, right? And then this is a foot, and this is half a foot. How about that? All right. So we have a 600 pound applied at this point. Let's say, make it simple for us. Let's say both AB and CD are made of same material, made of A36, for which the modulus of elasticity is 29 million psi, right? And they have the same diameter, so they have the same cross-sectional area of, let's say the diameter is 0.25 inch, right? The bar is initially vertical, and then when we apply the load, we want to find, now this problem is going to have two parts. Part A, we want to find tension developed in wires AB and CD. So I'm going to call them FAB and FCD, right? So this is another example of a statically indeterminate. So let's do part A and I'll do part B, which has to do with the deformation. So if you draw a free body diagram here, guys, notice that we have a pivot point, which we have a reaction EX-EY. We have the tension developed in wire AB, the tension developed in wire CD, and the load, of course, which is causing these tensions, right? So notice you have four unknowns, but as always for a 2D, 3 equations. So this is definitely a statically indeterminate problem, right? So one useful equation that we could use is taking moment about E. If I do that, I have an FCD times 3, right? Then I have an FAB times 1, right? Both of them going actually counterclockwise, positive, minus 600 times 2. So if I divide by 3, actually I don't have to divide by anything because I can't reduce it any further. I'll rewrite it like this. Okay? So this is one equation, but I need one other equation. If I could find that relates FAB to FCD, then I should be all set. And what would be that equation? That equation comes from the geometry. You see how this is the pivot point, guys? And then when you apply this load to it, this guy will rotate. Of course, I'm exaggerating here. And this would be delta of this point, delta C, and this would be delta of this point, delta A. I'll just put it here. And then using similar triangles or slope, you could say delta C over this, which is 3 feet, is the same as delta A over what? 1 foot. So therefore delta C is 3 delta A. Right? So like the previous problem, this is where we bring in the PL over EA for delta. So for example, delta C would be what? The force in, remember, CD times the length of it divided by, you know, EA. But of course, they're the same material. So for example, this one, we have what? We have FCD. The length right now, because it's a ratio, you could put it in foot, but it's really 12 inches when we want to actually calculate the deformation. So be careful with that, guys. Doesn't matter now, but later on, just be careful. Delta A is FAB times the length, which is 6 inches, half a foot, right? Again, if I had 1.5, it wouldn't change anything. You see how EA gets cancelled? Imagine if they weren't of the same material, you have to consider the difference, put the different values for E and area, right? So what I end up getting is that FCD is 1.5 times of FAB, right? And now this is my second equation. I can come here and instead of FCD, put 3 times 1.5 of FCD equal 1200. And I believe FCD, let's see what we get. We get 1200, I believe, divided by what, 5.5. So I guess I didn't do it correctly. Let's do it one more time. 1200 divided by this calculator is giving me a run around. 1200 divided by 5.5, 218, sorry guys. And then FAB would be this number divided by 1.5. See that? So we got the forces or the tensions developed in the wires. And now, if you want to find, say, the deformation of, let's say, wire AB. Let me just erase here and show you how we can do this. So for example, let's say you want to find delta B. So you say this is FB times the length, FAB, sorry, times the length of AB divided by EA. So the 145 that I got times the length. So now the 6 inch, okay? Unit becomes important. 29 times 10 to the 6, pi over 4. Remember, it was diameter of 0.25. And then you can go ahead and calculate this on your own. All right, problem number 2. I want to show you one more problem, guys, which will hopefully help you to see different types of, statically indeterminate, right? So in this example, I have a beam that is horizontal initially, right? Being held by 3 identical wires of same length, same material, and same cross-sectional area. So let me just call this A, B, C. And then let's say a load is applied here. Let's again put some numbers here, guys. 600 pounds. Let's say this is 2 feet. This is 1 foot. 1 foot. So the whole bar is 4 feet long. So wires A, B, and C are same area, same material, same length. After the 600-pound load is applied, you want to find tension in each wire. Okay? So let's draw a free body diagram. This is another example of a statically indeterminate. So we have FA here, FB here, FC here, guys, right? 600-pound load here. 3 unknowns, but only 2 useful equations. Why? Because the equation in the X is not used. So only in the Y direction, balancing the forces, which gives me FA plus FB plus FC equal 600, right? And moment equation. Take moment about any point you want. I'll take it about A. All right, so I have an FC times, looks like 4, FB times 2, and then a 600 times 3. Which actually, if you divide it by 2, if you want to do that, you get FB plus 2FC equal 900, right? So one equation here, 1, 2. Need a third equation, guys. That's again where geometry comes into play. But unlike the last problem, when there was a pivot point, we don't have that luxury here, guys. There's no pivot point. So now you have to say, okay, if this was the initial position of this beam, how would this deflect? Well, it would be combination of translation. So it's going to translate down like this and then rotate. So it becomes like this. Let's use a different color. So it becomes like this. The reason it will rotate like that because this load is applied on the right-hand side. So you get more deflection on the right-hand side. So this would be delta C, this would be delta A, and this would be delta B. Still no pivot point, but look, I can make my own pivot point, guys. Look. Look at this green triangle. What is that? Isn't that delta B minus delta A? What is that? Delta C minus delta A. See that? Now I can use similar triangles again. Delta B minus delta A divided by 2 is the same as delta C minus delta D, delta A, sorry, divided by 4. And then if you cross multiply, let's go back to black. So we have 4 delta B minus 4 delta A. Just multiply through. Equal 2 delta C minus 2 delta A. And then maybe even bring them to one side. 4 delta B minus, looks like 2 delta A minus 2 delta C equals 0. And now you put the equivalent of delta. I'll do it up here because I don't want to go to another page. Remember, they are of the same material, the same length, right? They have the same length, you see. I didn't even give you the length. Let's say they're 2 feet each, right? Doesn't matter in our case. So look what happens. What is delta A? FAL over EA. What is delta B? FBL over EA. Notice that I'm not even putting subscript for these, like length E and A. FCL times EA. So when you plug in for delta B, delta A, and delta C, actually you end up getting 4FA plus, or rather minus 4FB. I'm getting too excited, I guess. 4FB minus 2FA minus 2FC equals 0. And this would be your third equation. So 3 equations, 3 unknowns, 1, 2, 3. Solve it any way you like. No big deal, guys. You could probably use substitution here. Say FB equal 900 minus 2FC. And maybe even put it here. And then even put it here. And get 2 by 2. And then solve for them. All right, guys. So I was able to keep this video under 20 minutes. I usually make really short videos for the purpose of posting them on Blackboard. So this is eventually going to go on Blackboard. If you like this video, guys, as always, you can subscribe to my channel, and I'll have always new videos every week. All right, thank you for watching.